So we move on to the next realm, concept of rotational inertia. Okay. Well, I have already introduced this to you earlier, but anyway, we'll now look at it from analytical point of view and try to create the right mathematical framework for this. So as you can see here, every particle in the rigid body is moving in circular path. Okay, so that is something which we know. And now that means now you can see there's a rigid body here. It's moving. So I mean here you see the idea is there is an experiment being conducted here. This particle is being tied to a stone and it is rotated. Okay, first instance you take a particle is tied to a stone and rotated. So there is a tension in the string T bar. Hello.
Yes, sir.
Okay.
Yes, sir.
And there is force acting on this, right? Tangential force acting, and as a consequence, you can see these two forces acting here, and so therefore this. So in accordance with Newton's law, this force will create that acceleration in the direction of force, and the direction of the force on this particle is m into at. Hello. And T bar will be equal to m omega square r cap. That is P with respect to O. R bar is what? R bar is this vector. Okay?
Yes.
P with respect to O. We are writing it more clearly. Okay? Fine. Right? So therefore now R bar of P with respect to O plus F bar cross F bar plus R P with respect to O cross T bar. These are the two forces.
Yes.
So that means now you are taking the cross product of the position vector and the force vector. So what do you get?
Yes.
What do you get here? If it is static, you use the word moment.
Static is moment. Yes.
So since it is dynamic, we use the word torque. So this expression plus this expression will give you the total torque. Okay, the total torque it will give you. Now wait,
Yes.
don't ask question. Total torque. So we further write this as R bar P with respect to O into m A bar of T, suffix T, right? And R bar P of O cross of m omega square R P O. Okay, we write it like this. Okay.
Yes.
So the left hand side equals the resultant torque about O of all the external forces acting on the particle. See, there are two forces acting, so we are calculating the torque due to these two particles. So the vector product R bar P of O into A bar T, that is, what is this? This one. A bar T is tangential. In the first term on the right. So this one we know. R bar into A bar. So that gives you what?
Yes. R square A bar. Correct, sir.
How did you get R square A bar there? So
Sir,
because A itself is equal, AT is equal to alpha into R.
Yes,
Okay.
sir.
So you get there R square alpha. That is, see, and the second term of the both will vanish. Why? Because the cross product of T bar into this will vanish. Why it will vanish? Because R bar and T bar are making an angle 180 degrees.
Yes.
Sine 180 is 0. So this will not, T bar will not contribute to any torque. Only F bar will contribute to the torque. Okay. Fine. So what is important here is, we started writing these equations for linear motion. Okay, for linear motion. See, these equations were linear motion equations. We are using all the time. And now we from the linear equation, using the concepts of rotational motion, we were able to connect and get this term alpha here. Hello? And also this tau. Okay, so you have to appreciate the transition from linear mechanics to rotational mechanics. So summation tau bar at point O. See, this is important. Tau bar and with respect to O will be equal to m. M is the mass of the particle. R square, this distance, into alpha. Hello?
Yes, sir.
So now here, if you compare this equation with the equation for linear motion, so we used to write here summation F bar is equal to m into a. Hello.
Yes, sir. Yes, sir.
So m there was representing the inertia for translational.
Yes, sir.
That is opposition for transition motion. Mr square is for it should be interpreted as rotational inertia.
Rotational inertia. Yes, sir. Rotational inertia.
Anyway, I made it explicitly clear here. Translation motion. The total mass of the body in translation motion is a measure of its inertia. Mass is a measure of inertia. That's what I told you. To translation motion. Therefore, the sum of all terms mr square arising of all particles of rigid body provides suitable measure of its inertia to rotation. Inertial rotational motion, also called as rotational inertia, are more commonly called moment of inertia. So, moment of inertia, rotational inertia are all same. And I have already demonstrated that with some experiment here, right? So, you see, I can to lift this, so F is equal to m into a. But if I want to rotate it, okay, then I have to apply torque. So tau bar is equal to I into alpha. Okay, that is I am causing angular acceleration. Right? Fine.
Yes.
So I suppose the concept now is clear. That is, rotational inertia, translational inertia.
Yes.
Right. Now, this is something which I have already explained, but still, the measure of inertia in linear motion is mass. But the measure of inertia in rotational motion is a function dependent on the mass and its distance from the axis of rotation. Right? So, this also I have told you. That is, you see, if I hold it here at this edge and try to rotate it, I have to apply more torque. So, if I hold it here and I have to rotate, I have to apply less torque. Okay, that means now when I am rotating here with respect to this, I am holding it here. Then you see this, the entire mass here is distributed. That means now this is made of particles, it is distributed. From this axis, the particles are distributed far away from this axis, and therefore the inertia is more. So if I hold the axis here, the proximity of the particles with respect to this axis will be less, and therefore the inertia will be less here. And if I am holding at the center, the inertia is least. Rotational inertia is least. However, the translation inertia will not change whether I hold it here or here.
Yes.
Right.
Yeah.
Yes, sir.
Good. So here you see, this is assume that this is a rod and I have attached, there are particles M1, M2 here, M3 here, M4 here and all. So here the moment of inertia due to this is m1 into r1 square. This is m2 into r2 square, m3 into r1 square, m4 into r square. Therefore, if you take all these particles are attached to this rod and which cannot rotate, then the total rotational inertia will be equal to m1 r1 square plus m2 r2 square plus m3 r3 square plus m4 r4 square. Summation mi ri square. Hello?
Yes, sir. Yes, sir. Yes, sir.
Then what is the total mass of the system? m1 plus m2 plus m3 plus m4.
Yes, sir.
And what is the axis of rotation? A dash. Got it?
Yes. Yes, sir. Yes, sir.
Okay. Now, are you all? Did you all understand this? And
Yes, sir.
see here.
Yes, sir.
So the kinetic energy of each particle is half m v square. Since v is equal to omega r, so we can write the kinetic energy of each particle is half m. So v is equal to omega r. If you write, you will write it as half mr square omega square. So again, you see mr square has to be interpreted as rotational inertia.
Inertia, yes, sir.
Okay. Well, I want to ask you a question. Are you ready for the question?
Yes, yes, sir.
So, supposing this is the axis of rotation A dash, right? And in the diagram you have seen this is mass m1, this is mass m2, so this is r2, this is r1, and here there is m3, r3, and so on. So the total moment of inertia of all this about the axis A dash will be what? Okay, it is summation mi Ri square. Okay, so that becomes m1 R1 square plus m2 R2 square plus m3 R3 square. Okay, got it?
Yes.
Now, supposing instead of keeping the mass here, if I keep this mass here, okay, this mass I will shift it down by say some distance L. Okay, then what will be the moment of inertia about this axis?
Same, sir. Same, sir. Same, sir.
Sure?
Yes, sir. Yes, sir. Yes, sir.
Because that's what, huh? You should take the perpendicular distance
Perpendicular distance.
from the axis of rotation.
Yes, sir.
Yes,
Yes,
sir.
sir.
Done.
Yes, sir.
Done. Small question. Huh. Now, types of mass distribution. The system of particles can have particles that are discretely distributed, what I showed you there, like stars in the sky, or particles can continue, or otherwise, continuous mass. Okay, so here you see the mass is, the particles are so corrected one after the other, so I have to take it as continuous mass. Okay, so that means now let us see how we calculate the moment of inertia for rigid bodies, for continuous rigid body. Okay, so this is what is it. Okay, that is, see, now we'll start with a simple plate. This is a, okay, you can take a disc. This is the disc of mass m, right? Okay, so now since it's a disc, okay, I have not drawn it properly, please excuse me, right? So this has got what? What is this? Center, C. So center of mass.
Yes, sir.
Center of mass C is here, right? Now I am passing an axis through the center of mass. Okay, so this is C, C dash, something like this, right? And this is perpendicular to the disc. It is perpendicular to the disc.
Yes, sir.
Now, if I want to know what is the moment of inertia of this, moment of inertia of the disc with respect to the axis passing through the center. Okay.
Yes.
Moment of inertia, the body, the axis CC dash passing through the center. Okay. Then the way we have to do is very simple. You will take an incremental mass here. Incremental mass here dm, and you will take its proximity from him as something like Ri. Okay.
Yes.
Dm Ri. So therefore, the moment of inertia of this incremental mass about this point will be dm into Ri square. Okay.
Yes, sir.
Now, if you want to know the moment of inertia throughout, then you take it like this. Then you integrate it. Okay, over entire length. Okay, so this gives you what?
Yes.
The moment of inertia of the body about this point. Already we have discussed this. Okay, just that I'm mentioning it again.
Yes, sir. Yes, sir.
So you can see here that you get this like this. So most important is this one, you can treat it like, you can treat the moment of inertia of only this, that is dm into Ri square. You can denote it as di, that is incremental moment of inertia, just like dm, incremental moment of inertia. Here is the symbol I. And therefore, the total moment of inertia about that will be integration.
Yes, sir.
Clear, friends?
Yes, sir. Understood.
Very good. If you have any questions, you can ask. So, here, can you relate it to Newton's second law here? Okay, right. We'll see how this gets related with the similar to Newton's second law. Okay, see what I wanted to tell you here is that, so here you see we used to write the Newton's second law as F is equal to m into A,
Yes, sir.
F bar is equal to M by L bar. And now here instead of M we have got M R square. Okay, and instead of A we have got alpha, and instead of F bar we have got tau. So this is in consonance with Newton's second law. This is Newton's. See, Newton's second law is second law only. Okay. So what the first law says, that is with you need an external force to change the state of motion. That is first law, and the body opposes the change of motion because of its inertial property. Okay, that is first law. Well, the second law will say what is the effect of the force on the body. Okay, so the effect of the force is it causes acceleration. Now the fact of the matter is, now as I already explained this, now here you see, as far as the particle is concerned, wherever you apply force, in whatever direction you apply force, this particle will accelerate in the direction of force. Okay. However, if you say take this body, if you apply force, the line of action is passing through the center of mass, then it will only translate. Okay. Hello, are you with me?
Yes, sir. Yes,
So
sir.
if the force is applied here, okay, then it is not passing through line. Then this force will cause this body to rotate as well as it will translate. The body will rotate and translate. Both will happen.
Yes, sir.
So therefore, that means now this force will see two types of inertia. One is it will see the mass, okay, and it will also see the height. It will also see height. Okay, that is, if you say the force is applied here, and this becomes the perpendicular distance from the force, perpendicular distance from the force. Then here you see the R bar cross F bar. In this case, both are perpendicular, so this is RF. What is RF? This becomes the torque. Okay, and therefore the angular acceleration will be torque divided by the moment of inertia of this body. Moment of inertia of this body. Moment of inertia of the body about this axis. Correct?
Yes, sir.
No. See.
About the center of mass passing.
So now you see the important thing here is that you are applying force here. Now this, if this is pivoted at some other point, it will rotate about this point. And as I have already discussed this, if it is not pivoted about any point, then it will rotate about the center of mass.
Center of mass. Yes, sir.
Right? As far as the translated acceleration is concerned, it will be F by M will be A. So here you will get tau by I will give you alpha. So you will have to see both these things will happen because of the application of force. Am I done, friends?
Yes, sir.
Yes, sir.
Yes, sir.
Yes.
Right. Okay. Now these are all some small things which I'm sure you will be able to do it fatafat. So now you can see that there is a thinner rod. What did I say?
In the order.
Because I have not taken the lateral dimensions into consideration here.
Yes.
That's why I say it is thin rod.
Yes.
Yes. Now, what is the moment of inertia of this rod about this point? See, it can rotate about this point.
Yes.
So, so you choose an incremental mass here, dm. Okay. So dm you choose here. Okay, and its proximity from this axis will be r. So dm into r square will give you the moment of inertia of this incremental mass.
Yes.
Now this dm itself, if you see here, the total mass of this is m, and the total length, if you take it as L, then m by L will give you mass per unit length. Mass per unit length into dr will give you incremental
Yes,
mass.
sir.
Hello, everybody there?
Yes, sir. Yes.
Yes, sir.
So you substitute for dm using this, Okay, and therefore by substituting this, dm is equal to m by l dr. So you will get here r square, m by l will come out, m by l will come out, and r square dr. So r square dr will give you r cube by 3. Okay, and the limits are 0 to l. So 0 to l limits, if you put it here, then you are going to get ml square by 3. Did you get it, or shall I do it?
Yes, sir. Got it, sir. Got it.
Others, everybody there?
Yes, sir.
Because you have to do a lot of derivations, and I have already done this, I'm sure. So this is as far as the rotation about this axis is concerned.
Yes, sir.
At the edge. Now I have taken a rod which is free, and I would like to rotate it about the center of mass. That is, the axis is passing through the center of mass. The rod is like this, the center of mass is traveling like this. So the rod can tilt like this. Okay. So now the limits of everything is same. I have taken this incremental mass from this point at a distance r. At a distance r from here. So it becomes dm into r square. But the limits of integration will be minus, because I am taking this point here. So this side will be minus and this side will be plus. So this will be minus L by 2 to plus L by 2. The limits of integration. And again dm will be ml by dr. Same thing. So here I will get the moment of inertia will be ml square by 12. Okay, see, that means now you see, supposing this was a rod, then I can easily twist it here. Why? The moment of inertia about this point, which is this is passing through the center of mass, will be ml square by 12. I am taking a laminar, but actually it should be a rod. Okay, it should be a rod. Okay, I'll take a rod.
Yes, sir.
If I take this rod, take this rod at the center, it will be ml square by 12 less. This is ml square by 3 at the edge. Okay?
Yes, sir.
So, can you find at some other point moment of inertia or some other point?
Yes, sir. Yes, sir. We can do so.
You can do.
We can just apply parallel axis.
I have not yet thought, but you have learned in the college. Okay, done. So this hoop, so same thing here. So this is a hoop or a ring. So you will take an incremental mass dm here. So dm here will be what? If the total mass is m. If the total mass is m, and the total this is r. So this length will be 2 pi r. So dm will be m divided by 2 pi r.
2 pi r into d.
Okay.
Sir. Yes, sir.
Only 1 or 2 students are answering. So here, this is of branch mass m. This is a ring, a ring or a hoop. That is, this thickness will be negligible. If the thickness is not negligible, you can't use this formula. Remember that. Okay? In the second hoop. So here, this total mass of this is m. So if you take the total mass as m, then the dm here, if I take this dm, so dm will be total mass divided by 2 pi into what? Into this. Hello?
Yes, sir.
Into this. That is, see, this arc length, this arc length, if you take it as dl, into dl. Hello, are you with me?
Yes,
So the moment of inertia of this with respect to this point O will be what? So it will be dm into r square, because the radius is r. Okay, the dm into r square, and the total integration will be this. Now here, as far as the integration is concerned, so we are finding the moment of inertia of this about this point O. So here, if I substitute for dm, then m by 2 pi r will come out. So in the and even this r square will also come out. Now only thing is, it will be integration of dl.
Integration or dl.
Okay, integration of dl.
Or we can just
integration of dl. So integration of dr means id of dr.
Two
This is
pi.
simply
Two pi.
2 pi.
Yes, sir.
Isn't it? So you get here this r is cancelled. So you get here mr by 2 pi into 2 pi.
Yes, sir.
2 pi
Yes, sir.
you will get here m.
Yes, sir.
Yes, sir.
You
Yes,
don't
sir.
have to do r theta here. Okay, you can directly do like this and do it.
Directly can. Directly. Yes, sir.
So for instance, so you get here mr for a
Yes, sir.
So for a disk, so I think I have already done this in my class. You get here mr square by
Yes,
2.
sir. Yes, sir. Yes, sir.
I have already done this. See, only thing is dr. So dr will go from 0 to capital R, the limits of integration. So you get mr square. So for a disk, it is mr square by. Now one more thing I am telling here. See, you should not get confused. See, I will give you a lump of mass. Lump of mass of m. I'll give one lump of mass. Okay, and with this mass, I will ask you to make a ring. So you will make a ring. Okay, so this will be the radius of the ring. Remember. Okay, with this mass, I have made a ring, man.
Yes, sir. Yes, sir.
With the same mass, I will ask you to make a disk. I will ask you to make a disk. Okay, so
Yes.
the disk will be small, isn't it?
Yes, sir.
So this will be the radius of the disk. Got it? With the same mass.
Yes, sir. Yes.
Okay. Now you see what is the moment of inertia of this m r square.
Yes, sir.
What is the moment
Yes,
of
sir.
inertia of this m r d
ID
square
square.
by 2?
Yes, sir.
Because everywhere in the formula, they will write what is the moment of inertia of this mr square. What is the moment of inertia of the disk mr square by 2. So therefore, moment of inertia of this is twice of this. No, this r is different, this r is different. Unless they specify both r's are same.
Yes, sir. Yes.
Understood?
Yes.
Unless they specify. So remember that this is for this is for this. Okay?
Yes, sir.
Keep that in mind.